Hi everyone, this is going to be the lecture about the line integrals of a vector field. So first, here's the motivational question. But before you listen to this lecture, you make sure that you listen to the other lecture about the line integrals of a scalar function along a path. And this is line integral of a vector field along a path C. Okay? But you need to understand that first to understand this part. So here's the motivational problem. From there, this notion rises naturally. So this is a xy plane. And we have constant gravity here as a vector. So we're going to put the gravity up there as a vector. And we're throwing something with initial velocity v0. So it's going to have this projectile. But let's say we're only looking at this portion of this path, which is P and Q. It could be certainly the whole portion, but suppose we're looking at this direction. And it is moving to a certain direction. So this line integrals of a vector field is a little bit different from line integrals of a scalar function. This one is actually sensitive to the orientation, but it's not yet sensitive to the parameterization, but it's only sensitive to the orientation. So as long as you're going from P to Q, this integral will be the same. But Q to P will have a same magnitude, but it's going to be opposite sign. But as long as we're going from P to Q, how you parameterize from P to Q doesn't matter as long as we keep this orientation. So that's what this line integral is. So here what we would like to calculate is work. So this is going to be the work calculation. And we're going to review this work calculation, simpler situation you might have learned from Calculus 1 or Calculus 2. So here's the present point A and point B, and we're moving a certain object from point A to point B linearly, and we're using the force in the same direction as we are, and it's this moving, so distance apart, so let's say it's d units apart, and magnitude of the force is F. Here's the magnitude, therefore it's a scalar. So everything is pointing in the same direction, so the vector information is not important. The work is defined as this magnitude of the force times the distance it moved. So that's the definition of the work. So what does it represent? It's kind of, for example, if we're doing this work and this quantity might represent fuel usage or energy that requires to do this thing, something like that. So that's roughly what it represents. So we're going to use this idea to calculate the work done by the gravity. So this is going to be a free fall, so I'm going to writing underneath this projectile picture, and I'm putting this square here, the free fall. So no other force is acting on to this object. So we're tossing it with a velocity v0, and after that, it just follows the gravity force, the constant gravity. So it's a free fall. So only the gravity force is acting on it, and we're about to calculate the work done by the gravity. And that's the only force that's applying there. So here's a magnified picture. So we zoom in. This pk minus 1 and pk is 2 points that support. So we're dividing this arc P and Q into many pieces, and this is, let's say this is a kth interval. And what we're going to look at is this velocity vector v, and we're going to look at, starting from that pk minus 1, we're going to look at this gravity vector f, and also there's this gravity vector f. Although this is slightly curved, and when they're very, very close to each other, we can kind of approximate this one with just a v vector. So pk, although in this picture it's slightly off from the vector v, we can assume when it's very close, it's almost on that v. And of course, we're going to assume some constancy there. So one approximation one assumption is that pk minus 1 and pk, that's almost a straight line. And force that is acting on, exerted in the direction of the line that is extending this vector v, is always changing. This gravity vector itself is pulling it down all the time, but the amount of force that is exerted along this direction of v is always changing. Okay? It turns out what is important is the amount of force that is exerted along this direction is the only thing that matters when you calculate this work. So although gravity is keep pulling it down, how much work was done along that direction is the projection, and that's what we're about to calculate. In the next pages, we'll look at different examples to see the meaning of all this thing. But right now, let's focus on what is it that we're calculating. The answer to that question is that we're calculating the projection of the gravity vector f along the direction of v. And the gravity vector is always pulling it down, but you can see from that picture up there, this velocity vector v is actually constantly changing. So that's why we need integration and Riemann sum. So let's think about the projection pictures and putting this pk minus 1 position there again. So that's v, and there's a gravity vector f. And pk minus 1, I'm going to pretend it's almost there on the vector v. Actually, vector v is pretty long, and pk minus 1 is very close to each other, but this v is a velocity vector, so in general, this is a lot longer vector than the pk minus 1. And we extend it here. So the projection of this f will be this vector, so you may use this wiggly line. So that much of the force is actually applied along the direction of f. Okay, if this, for example, if it happened to be perpendicular, then no force is at that instant it's applied along that direction. So we want to use this force to calculate the magnitude, the work done at that moment. So let's recall the projection formula, projection of vector f along this direction v. So it was given by following formula. First, because it's projected onto v, that must be an integer, the scalar multiple of v, and the scalar multiple look like this dot product fv divided by absolute value of v squared. That's the projection. What we need is not the whole vector, we just need this length, and which is represented by component vector. And component vector f of v is a magnitude of this one, but it's a signed magnitude. So in this case, if v and the projection of f is pointing oppositeward, this component part will be the length of this vector projection minus. If you think about this object that is coming down, it's kind of pretty much velocity vector is pointing the same as the gravitational vector. So in that case, this f and v is not wide like this. It's going to be forming an acute angle, and then it's going to be positive component. The formula is that if you put absolute value around this vector, you only pick up one copy of v. Up there, we keep this f dot v, which can be negative. So that's the formula. That's how much force is exerted along the direction of v, or the opposite direction of v. So if I denote by wk the amount of work that is done at that instance, assuming that time period, or between pk and pk minus 1, will be this constant gravitational force, and then let me use this vk, tangent vector at that moment, times distance. Distance is sk here, arc length. So if we add up all this, and that is supposed to be the total work. So I'm going to write down the idea of the total work done by the gravitational force must be very, very close to this sum. Sk there. So this looks a lot like line integral. Only problem here is that definitely f of x, f is a function of f of x, y. But v, if you think about the v is not quite the function of f x, y. V depends on how you parameterize this thing. If we're going through, of course, in here it's a gravitational force is completely determined, but in general, this is not quite the function of x, y. It is more of a depending on the parameterization. But because of this absolute value of vk, it actually turns nicely to something that does not depend on the parameterization. This vk is a tangent vector, and if you divide it by its own length, it's going to be a unit tangent vector. So that is denoted by like this tk. And this one doesn't depend on parameterization. It actually does depend on, although, the orientation, depending on orientation. So as long as we have this orientation, sorry about the spell, this one is a function of xy, completely determined. It's better. So we're going to switch this one to k equals 1 and f times that whole vk, f sub value vk, because that's a scalar multiple in the denominator there. You can put anywhere. So that changes to tk. That's the dot product of two vector field by sk. Okay, then you can, this is a function of xy with the orientations given. Then you can switch this one to the line integral because this is a scalar function. The wiggly part is square scalar function. So this will approach the line integral of this scalar function, which is this dot product ds. Okay, so that's this is it's going to be the total work. And that's actually how they define total work done by force field F, and where this T is a unitangent vector of an oriented curve C. So that's the difference, and we have to just talk about the oriented curve. So the line integral, this is called the line integral of a vector field F along an oriented path C. That's the introduction. So that's the definition of this line integral of a vector field. So what we really did is that we take this vector field and then dot it with this unitangent vector and turn that into a scalar function, and then we did the usual line integral of a scalar function along AC. In that way, in that process, to define this unitangent vector, we needed this orientation. All right. In the next page, I'm going to give you a more straightforward definition of this line integral. So this whole page is for the motivational part. Okay. Okay. Let's look at the formula. That was the motivational problem to define line integral. So let me just make sure that I clarify all the context first. So that's the motivation. So here's the definition again. This definition doesn't require force field or anything, or gravity or anything. Just a given vector field F and a path C. We defined this line integral of scalar function f dot t ds to be the line integral of vector field f along C, okay, where t is a tangent vector, unit tangent vector, sorry. Right, if you purify it like this, one thing that part's unclear is this about f is clear, and then the curve C is given. But when you think about unit tangent vector, You don't need a parameterization to identify a unit tangent vector, but you need at least the orientation. So what we have to do is a given f and a path c, so it should be oriented path. So that's an important part. This definition is not sensitive to the parameterization, but it is sensitive to the orientation of the parameterization of a C. So when we specify C, you have to give the orientation of the C. It's going from where to where. All right? If you state it like this, your definition, there's nothing ambiguous in anything. The T is uniquely determined by this whenever we have oriented path C. So conceptually, everything makes sense. But let's think about how we're going to actually calculate all these things. So we go back to this formula. The C and ds can be written as the C and ft all changes to dt. We change to d8, t8 to tb, and Jacobian factor r prime to t. This all makes sense whenever we have a parameterization, right? So C is parameterized by x equals xt, y equals yt, and we write rt as with this component xt and yt. So this is from earlier lecture. If whenever you have a line integral of a scalar function, here the scalar function is this f dot t, then we can turn this one into a dt integral usually like this. Okay? So what we have to do is at this point here to get rid of this t, so f is usually given as a formula and we have a parameter r prime there, so goal is that getting rid of the t so that we can conveniently calculate this. So what is t? Is this tangent vector divided by its own length. So it's a tangent vector and it's a unit vector. So that's the formula. So that makes the earlier property, this ft, the integral, line integral, dt here, is equal to a to b, one variable integral ft dot t, which is, sorry about that, let me do that again, f dot t is now replaced by r prime divided by r absolute value of r prime, that's dot product, and out there absolute value of r dt. Because this absolute value of r, absolute value of r prime, there are scalars, we can cancel those. So when you cancel that, ab is an f dot r prime dt. So that happens to be the formula. So here, f is given explicitly, and r prime is a parameterization, and differentiating is not much of a work, and do the dot, and integrating with respect to t is actually this line integral of the vector field. So t disappears and everything is in terms of r, so it's a computable formula. It's a practical formula. Okay? So before I move on to the actual example, let me introduce one more notation. So that's the line integral. That's the definition of a line integral, but here's a notation. If we write this r prime dt in ddt notation, it's going to be ab, the vector field, and dr dt is the second vector in the dot product, and dt out there. In Leibniz's notation, and when you do substitution rule and stuff like that, we often treat this dt, dr as if it's constant, the quantity, and cancel whenever when you switch the variable of integrals. So if you want to do that freely, and of course that's just nonsense at this stage, but using that notation, we're looking at it here, we introduce the following notation. So f integral is there, f is still the vector field, and it seems like we have a dt in the denominator and dt in the outside. If we cancel those two, as if these are scalar of this vector dr, then we're left with this. And the dt part's gone. So they thought it's a good notation and switch it back to line integral notation C down there. So they introduced this notation. Whenever you see this, it means line integral of a vector field f along C. And R here represent the position vector of a C. So these are the notation. Here's some examples. Let me write it a little bit small so that I can fit this one in. So suppose we have force vector field is given by x squared minus xy. X squared is x component and negative xy is the y component. And the path C is not given by Cartesian equation, it's actually given by parametric equation. So it comes with the parameterization, the orientation. It's a sine t, and then t is varying from 0 to 2 pi. Okay, so they wanted us to calculate the work done by the force field. Find the work done by the force field. Okay, first I'm going to formulate this as integral form and calculate it and come back and explain the meaning of this one once again about what we mean by work done by the force field, because this path here is not the free fall under this force field, but that's how I actually introduced at the beginning of this whole calculation. So I'm going to interpret this one correctly so that it is kind of slight generalization of what we were calculating before. So here's the shape of a C. So we've seen this a lot, cosine t and sine t, that's a circle. So the circle starts from here and there, that's where the t equals 0. And t equals pi over 2 correspond to this top part. So that's the C, and t varies from 0 to pi over 2, so that's the orientation. So it doesn't depend on, again, the parameterization, but at least it depends on the orientation of the parameterization. If you change the orientation, it changes the sign of this the calculation we do. So the work done by this force field is simply this one here, is Ft ds. Okay, F is a force field, and t here is the unitangent vector along that direction. So that's the very definition. Actually, how we calculate this is going from 0 to pi over 2. If you look over there, our formula, which is in the formula line, if you look up there, I'm putting the star right now, 2 stars, all right? That's our formula. So Ft, sorry about that, that's not our formula. It's wrong locating where the formula was. So here's our formula. The 2 stars is erased and located in a new part. It's kind of in the middle. It says practical formula there. That's our formula. So that's what I'm doing here. 0 to pi over 2, and f and r prime is what we have to put here. So what is r prime? We have a formula. So it's negative sine t, comma, cosine t, right? And dt. And that's the formula. So that's the derivative, and this is time to replace this f with the actual formula, 0 to pi over 2. What is f is x squared, so x is now cosine t, you have to parameterize it, so it's a cosine t squared, minus x is again cosine t, and y is sine t, dotted with this negative sine t, cosine t, dt. All right? So if you dotted these two, is 0 to pi over 2, x component and y component together make this one cosine squared t, sine t. And plus, but there's a negative sign, and cosine squared t, sine t again, dt. So this is integrable, so I'm running out of space here, so I'm going to stop it here to calculating this work calculation. Okay, but let me go back to and remind you the meaning of this one. The particle is moving from t equals 0 position to t equals pi over 2 position, not because of the force field. The way to interpret the meaning of this calculation is that, for example, as follows. Suppose we're moving this particle at t equals 0 to this position t equals pi over 2. And as we do that, if there's no other force field, we have to use our own force to move this one to that. But if there is a force field, the force field will do something about our motion. For example, at some point, the force field is, for example, I'm going to draw it over here in extra space. And suppose this is actual motion of the thing, so we're trying to move this one to that direction. But suppose at that position, force field F is actually creating this much of the force at that position. So, but we're trying to go to this direction, the opposite direction. So the force in that case is not quite helping us to moving forward. So the meaning of this calculation is that at total, and what is the work that this force field is contributing to our motion from t equals 0 to t equals pi over 2. So without it, we have a certain amount of work you have to do to move this t equals 0 to t equals pi over 2. But if all of a sudden, if there is this force field appeared, and then is this helping us or not helping us? In the total, you calculate this one. So if I skip the calculation, it turns out this quantity is negative 2 over 3. What that means that total, this force field is not helping us to moving this particle from t equals 0 to t equals pi over 2. The contribution from this field when we're doing this work is negative, so it's not helping. So, for example, if you go back to this square picture again, there is this point of application, and contribution from this force field is opposite direction if you project it down. And the next moment, if you switch the direction, maybe it's helping us to pushing forward, so we require less force to do the job, and something like that. So the true meaning of this calculation is again the contribution of the force field to along the contribution of the work contribution of the work from the vector field F along the path C. So that's a way to interpret this calculation. Let me introduce another important example, and then I'm going to introduce a notation, and that's going to be probably it for this lecture. So this next example might help you to understand the meaning of this old calculation one more time. So for example, like this, suppose there's this rod or string, and there's a little bead that's tied together, but it has a hole so it can move around. And suppose there's this electromagnetic field is generated. It creates everywhere constant force to horizontally. But this bead had no choices. It had to move. It had to stay on this track, on this rod or string. So think about this two different situations. Here's this string or rod again. There's this bead in there. It happened that magnetic field that generated force is perpendicular to this rod. Let's see what happened in there. So we're not going to touch this bead, this little string, this little marble, that's or whatever that you want to call, bead that is attached to that. We're not going to touch that. It's only this the force field is going to acting on that and move it here. If you look at the second picture, because it's perpendicular, turns out the component of the force vectors that's applied to this rod is nothing because it's perpendicular. So you can imagine if you just keep pushing it, whatever, if this is the metal part and use a magnetic bar to try to push this one this direction, it's not going to go anywhere because it's stuck to this rod. But if you change the direction like this in the first picture, there will be some component part is there, the positive component part is there, it's actually going to begin to move upwards. So how much is that force is going to apply to there is exactly the component for that. If we have a direction v, then the component part is exactly F dot v divided by v. All right? That's exactly the component. The v is a constant, and we assume the F is always constant, so this is going to be always the force that is applied along the direction of v, and in this case here, the force applied along the direction of v is always 0. So if this force moves this thing to a certain distance d, and that's the work done by this one, and here the work done by this force field is a 0. Another means is 0 work is coming from force field. But if you look at the first picture, there is some contribution. So if we're actually trying to touch this one and try to move it along this rod, and there is some help coming from this force field, so you don't need a whole lot of force to actually, less force than you're just pushing it in this situation. Okay? So that's what I mean by contribution. So the work we're calculating can be interpreted as a contribution from the force field. Here's some interesting notation they introduce, especially for this line integral of a vector field. So the vector field line integral is defined like this as a line integral. And then I just introduce this notation also is f dr. These both are just a notation of a line integral of a vector field. But the actual formula, to recap, is that the following. This line integral of a vector field is actually equal to the integral from a to b of vector field f times r prime t dt. This is how we actually calculate where r is given by x and t. So let's write it in general. A to b f dotted with x prime and y prime dt. And to write it further out, we need to specify the component of f as well. So f has component p and q, therefore this p and q are scalar function. Together makes a vector field, but p and q are scalars. So if you dot this pq with this x prime and y prime, it can be written as like this: ab p dx dt. These are two scalar multiplied, and q multiplied to dy dt. And everything is an integral over dt. So this is actually the part you go through to calculate this integral. But here they wanted to introduce another notation because they see this dt cancellation. So here's a notation. We cancel this dt, and we're going to write this line integral of a vector field, ds, as a line integral from p dx, where after you cancel this dt, there's no t in there. P is indeed the function of x and y, so you can just treat everything in terms of x and y. Since there's no t, they want to use this oriented path c in there, and plus q dy. So this is a notation. So whenever you see this, and you have to interpret that as a dot product of something. So here's an example. So this integral is called the line integral. So let me separate this one of the thing, so they can separate it here. Also introduce just this part dx. And what is the meaning of this one? You have to introduce a notation. That's exactly the parameterization a to b, p, dx dt, dt. This is not a dot product itself, it's just two scalar multiplying each other. It's a part of the dot product. So this integral is defined like this. And the other part, c, can be separated, and meaning of this notation is this one variable integral q dy dt dt out there. They're all scalar function multiplied each other. So these integrals are called the integral, line integral of scalar function along c. Seems like nothing's different, but only what you're multiplying at the end is not ds. So to distinguish that, they call it with respect to x or with respect to y. But if you look at all the other integrals we did before original notation, these are all integral with respect to arc length. So that's the term they use to distinguish this. So I'm going to go to the next page to give you an example of this thing. It really requires example to get used to this notation. So here's an example of what we have just introduced. So I haven't introduced any three-dimensional thing here, but I don't think you will find any problem. Everything is described as vector and dot product, and all these things can be easily stated and understood in terms of three-dimensional vectors. So I'm going to pass to a three-dimensional example and hope you find this understandable. So let's look at this line integral xy dx plus x minus y dy, and c is the line segment from 2, 0 to 3, 2. So we don't have a parameterization, but we at least were told that how it was oriented. So that's important part. So we're going to first sketch. We're going to calculate this one first, and well, actually all together we're going to give the meaning and so on. But we're going to sketch the c first. Y there, and x-axis. 2, 0 is over here, and 3, 2 will be somewhere over there. So that's the line. So I'm going to label A and B, and this is the direction. Because it's a straight line, we can parameterize using the vector 2, 0, and the other one was 3, 2. So what is this directional vector? And using that, we can easily parameterize this line, which is it's a column vector. It's x coordinates 3 minus 2, so that's going to be 1. 2 minus 0 is a 2. So that's the directional vector. So if you scale this one, t times v, and you're going to reach all the points in between, from A to B. If t equals 1, then it's going to reach B. When t equals half, it's going to reach the scalar vector will reach exactly in half. If t is 0, it's going to shrink all the way down to the 0 vector at A. But as you can see, we have to do something about this point of application. So the real R, t, is that not only just the TV, but it must have the point of application 2, 0 added. So it starts from 2, 0 and go along the direction of by the scalar factor t. So here, if you multiply t, you got t and 2t, 2 and 0. So altogether, you can see xt is t plus 2, and yt, there's a 2t, where t varies from 0 to 1. And this is the parameterization of that line. All right, so let's think about these objects. before we just go and calculate, we'll do one more thing. What on earth does this mean? Is that you can manipulate like this as a dot product form. So you can separate that xy and x minus y. Those are the coefficient of dx and dy. Then you can write it as a dot product form like this, dx, dy. That's kind of the part that corresponds to dr part. But once you write it like this, you know it's a dot product of two vector fields. The r is coming from the velocity vector, and this one is the force vector. So although there's no force vector, nothing, it's just a straightforward calculation of this line integral with respect to x and with respect to y, but you can interpret it as the line integral of a vector field like this. Therefore you can interpret it as a work done by this force field, where the force field is given by xy comma x minus y. Again, like I explained before, the motion going from A to B is not the net free fall along vector field. We are artificially moving this point from A to B, and this calculation we're about to do helps you to figure out how much of a total work is coming from this force field. The contribution from that is what we are calculating. Another way to put it is that suppose there's no force field and we have a certain calculation, and the work required going from A to B is a certain amount. So that kind of represents fuel usage or energy that is associated to this part. But when there is a force field like this, it is maybe, if it is totally positive, it means it's helping the work was served or contributed by this force field is helping us, so that we don't need a whole lot of and less energy. If it is not, then we require more energy. So that's the interpretation. The contribution of the work from this force field is what we are calculating. All right? So that's all that meaning, but to calculate, it's straightforward. You go back to the original formula, and here, change everything in terms of t. So t varies from 0 to 1, so this line integral c notation changes the integral from 0 to 1, and x is replaced by the parametric equation we have there, and y is replaced by that, and dx is replaced by dx dt. And x minus y, x is t plus 2, and y is negative 2t. Y is 2t, but there's negative there. And dy switches to dy dt, and dt out there. So I'm doing this here for the first time, so I wrote this dx dt like this, but when you do it, you can skip this part and directly substitute what you see from your parameterization. So it's a 2t, t plus 2, dx here is just 1, and plus simplified version will be 2 minus t in there. And dy, if you look at the parametric equation of y, is t is 2, and dt. So this is a integral you can do it yourself. So that's pretty much what I prepared for this lecture.